Hello. However we move the panels, the parity remains always the same, even. Hello. Welcome to Python Challenge for All. Okay, let's continue our work, a journey about on 8 puzzles. Okay, so last time we almost completed the making of the sliding game, 8 puzzle game, and tried several possible combinations of panels that we can solve. And then we found that there are unsolvable boards. Yeah, whatsoever we can do, we cannot solve some configurations of puzzles. And what kind of boards are unsolvable? That was kind of homework. Okay, let's continue our journey. So today we're going to generate only solvable games. So okay, let's see what the conditions for the game to be solvable. And okay, so if we go to Wikipedia, for example, we took some looks at sliding puzzles, the more general names, and more specifically 15 puzzle. And the smaller version is here. It says 8 puzzle, which has 8 tiles with a 3x3 frame. So here, there are some mathematical analysis about solvability. Okay. If you're interested in this kind of thing, you can take a close look at it. There, we can see that the puzzle is solvable only if the permutation of the remaining pieces is even. So here, okay, here I will take a very easy way to determine the condition for the solvability. So here I say 8 puzzle is solvable if and only if inversion number is even. What is inversion number? Okay, inversion number is a number of elements, number of panels that are out of their natural order. Okay, let's see. Here, inversion, also part, yeah, here the description in the Wikipedia, discrete mathematics word. So inversion is, well, yeah, of course, if you're interested, you can read it. But simply said, it's number of elements that are out of their natural order. So I say if the number of panels that have greater numbers with smaller indexes that are the sum is infinite. So let's try this and find if we can use it for solvability conditions, solvability determination. So let's go. So here in this code, we define a function to determine if a board position is solvable or not. So to do that, let's say here, define a function, diff invenum, given a board position. Yeah, board is 3x3, okay? It's a kind of list of 9 numbers through 0 to 9, 0 to 8, okay? So, for example, one way is to initialize an counting C, okay? Counter C to be 0 and, okay, make a board of i's for I in range, say, 9, nn by nn, okay? If the board, okay, yeah, again, then let's check all the panels that those whose indices are smaller than I. So for J in range starting 0 to I, a little before I, okay, until up to I minus 1. And if the we don't count the 0 panel, empty panel. So if the J panel, yeah, only if J panel is not 0 and J panel is greater than I. Okay, so this is if in this case we count up the number by 1. Okay, so this is all about invenam calculation. So we initialize 0, and for all the panels in the board, check all the panels that are left or smaller position to I. And then if that's non-zero and that number is greater than the I position number, then count it and then return it CC. Okay, so how can we use it? We can use it after, say, new game generation. Okay, if just print. Okay, let's just calculate inam equals invnam and this board position as the argument, and the return value is inam. All right, let's print the inam and board, and let's check that. Okay, let's run it to see what happens. So here we say the board configuration is this, and the invnam is 16, which is even. So I say it's solvable. Okay. If it's okay, let's do it again. In this case, okay, let's do it again. In this case, 626, again, even, so solvable. Let's do it again. In your case, maybe you have some odd cases. This is odd. So this game is not solvable. Let's check that for simple cases. If the position is the, say, 5, 6, 7, 8, 0, the goal position, okay? The goal position, in this case, the invnam is 8. So this is solvable. This is strange. What's strange? It should be 0. Okay, what's wrong with this should be I. Okay, sorry. Okay, board I is not 0, and the smaller the boards to the left has bigger numbers. So then count up. Okay, let's do it. Sorry. So in this case, it's 0. Okay, what happens if you switch these two numbers, 8 and 7? And in this case, inversion number is 1, which is odd. This means this one is, unsolvable. You can see that. So we can check if that okay, so we can write after making a game if the game is solvable or not by here, maybe okay, if in inam %2 is maybe ng. Okay, if it's 1, it's ng, else okay. So this is a very easy way to check whether a board is solvable or not. This is ng. Okay, let's comment this out and run it randomly. This is solvable. Again, let's do it. This is ng. Okay, So maybe this is the easiest way. Another way is using list comprehension. Actually, this is too redundant, so we can write it if you want as return. No. Yeah, just use list comprehension to calculate this. Can you do it? Maybe you can do it by sum for 1 for I in range nn, and then for j nn j. And if this is the simplest way to write it, to have the same thing, you can check it yourself. And then you can return it. If you want, you can make change lines here. So this is actually good also. This will give the same thing. Okay, return. What's wrong? Return. Okay, return. So this should give the same thing. 11 and G. Again, do it. 11 and G. 9 and G. Oh, all those NG games. Okay, 18. Okay. So this is a very simple way to find out if a game is solvable or not. Okay, check the inversion number at each panel move. Let's show that we can check the invnum. Let's copy it. After each move panel. Okay, here we move panel, and here after each move we can show that, okay, print, say, self step. Yeah, let's make in F string. Self step, curly bracket, self step colon, and then in inum, so that we can check that after each move, the inum remains invariant. About the parity, okay? You say parity is the word for checking whether it's even or odd. If the parity is even, it's solvable. If it's odd, it's not. So let's check. What's wrong with? Okay, here. Let's check that every time we move the board, okay, here. Okay, let's look at here. So if we move the board, the inversion number is 10, remains 10. So there is no change. Oh, here, we changed, but from 10 to 12. So remaining, so however we move the panels, the parity remains always the same, even. And that's all. That's actually the same for unsolvable games. Okay, let's exit from it and run it. This is NG game. Still, if we move the panels, you see that the parity remains odd all the time. So unsolvability holds whichever panel we move and how many moves we make. Okay, so you can check it yourself. Okay, so this is how we can check the inversion number at each panel. So the last thing is when we generate games, shuffle the games and skip in unsolvable. So maybe we can make the new game function to generate only solvable games by making a loop here. Okay, so in new game, we make for, say, I in range, maybe 10 times is enough. Sorry. 10. Sorry. And then we, okay, let's see. Yeah, we skip it. I indent it so that, yeah, if only if inum is okay, even, let's break from the uh, from the um, loop and yeah, make the game start. Okay. Otherwise, we will do the shuffling again until we get solvable games. So this is maybe a good way to try several times, up to 10 times. So we have, yeah, actually the probability of generating solvable game is 50%, 50 by 50. So we had solvable game after 2 trials. In the third round, we had solvable games. And here, maybe we can have better configuration. So maybe in the next time, I will tell you how to make, um, how to solve games. Okay, in this case, you can see that after 37 steps, we completed the sliding and reached the goal. And if you look at the history, yeah, as you see, always the parity has been all the time even. And at the last state, the goal, the parity is even. So this doesn't happen for NG games, unsolvable games. Okay, so this is what we do finish today. Homework. How can we solve a solvable game? I will give you a hint next time so that you can solve solvable games very easily. Okay, so be sure to come back. That's for all today. Thank you. See you next time. Bye bye.